are now going to stay within HPC, but we're going to go a level deeper to the silicon itself. So in other words, from silicon to photonics to quantum, the processor architects that will define Europe's next era of computing. And this session will too be moderated by an individual who I think has been a DTM supporter from day one. In fact, she was moderating a fireside chat, if I believe correctly, last year, and that is none other than the VP Communications at Early Bird Venture Capital. Please welcome Ellie Marcus.
Thank you. Is this on?
It's on.
All right. And amazing. All right. Hi, everyone. Well done to our audience for selecting this particular session where we're covering one of the most critical topics for the future of computing, the European semiconductor stack. My name is Ellie Marcus. I'm VP of Communications at Early Bird, Pan-European VC, and proud supporter of DTM, as mentioned. And today, we are joined by 4 experts from across the stack, as you can see. And we're going to explore where Europe can leverage its strengths and the full value chain. So here's the format. Each speaker is going to present about a 10 to 12-minute insightful talk, walking us through the stack from precise manufacturing to innovative new materials to AI acceleration. If we can, we're going to ask some questions along the way, and we're just going to get started. So I'm going to begin by welcoming Michelangelo Massini, who is Head of Research and Technology at Zeiss Group. Zeiss is known for world-leading lithography optics used by the chip industry to manufacture semiconductor equipment. Notably, I think this is interesting, they dedicate 15% revenue to R&D, which is an investment into the future. So please welcome on stage Michelangelo. And you
thank you. Thank you very much, Ellie, and thank you for having me here. And it's a great opportunity, and I've met so many innovation leaders. And maybe a starting question to you: what would you do? And think about your innovation portfolio, your product portfolio. What would you do if there's a technology that can reduce the cost of your product by a factor of 10? Would you be able to adopt this technology faster than the competitor or maybe some startup? And nowadays, in this time, we are facing so many technology waves coming up, rolling towards us. And I'm not talking about AI. That's, I think, the most impactful and biggest technology wave. Today, we go into the photonic integrated circuits. And I will show you why it's also relevant for Zeiss. To give a little bit of context why I'm talking here representing Zeiss, we are a 12 billion revenue company, and with these 4 segments, then all of them are relevant or we are producing products with photonic solution in semiconductor manufacturing technology, industrial quality research, medical technology, and consumer markets. Ellie, you mentioned already to stay shaping with innovation in all of these fields, we reinvest always every year 15% of our revenue in innovation. And you can imagine, so I have, I think, the quite best job on earth, being able to do the early stage innovation with this impact. I think semiconductor is well known. I think everybody of you has a piece of this technology in your pocket, because every single CPU in this room has seen the light of the day through our photonics and optics. Another example, medical technology. I was 8 years in R&D in medtech. We can enable the neurosurgeon during neurosurgery, for example, extracting the tumor out of the brain, to see the invisible tumor in the brain. And you really want this neurosurgeon to do the right decision to decide, okay, where to cut and where not. So if you look now a little bit back in the past of of Zeiss, and it's always helpful to look back and learn from the past. There was a lot of technology waves, and Zeiss was not always an innovator. We took also often the role of an enabler or adopter. Sometimes also we get disrupted by some technology. And I think it's on you as technology leader always to try to understand, okay, what do we do with this new technology? Which role we gonna take? And for us, especially if you are a company with a big legacy, with a lot of old and important products that you cannot, you don't want to disrupt, but they cost a lot of energy. You have to be ambidextrous and do the legacy stuff, but still always be explorative. So we decided to check and to invest in the new technology waves. We decided to start this Beyond Innovation vehicle, and with this Beyond Innovation vehicle, it's looking beyond our existing core business. The core business is sure, okay, we know exactly what is needed for our customer, what can we do. We have methods and processes to ensure that we are on the technology roadmap on the right way. But this is focusing on the existing core business. If you want to go in new markets and new technology fields, we introduced this Beyond Innovation vehicle. And let me, for example, the Beyond Market fields, it's more, okay, we have an existing competence in technology, for example, spectroscopic sensors, and we can apply this in complete new markets like agri-tech. And today I want to pick one beyond technology fields. There we really search for paradigm shifts, and photonic integrated circuit is a paradigm shift. For Zeiss, very specific because it impacts every single business. And then we set up a team, a fully dedicated team, give them 10 million to start, and then if they prove that this is a relevant topic, we invest other 3-digit million amount of budget in this topic. And so we have done in photonic integrated circuit. Other topics are also synthetic biology. Maybe it comes next, laser fusion energy or optical computing. And now if you look on photonic integrated circuit, why is this so relevant? Photonic integrated circuit integrates a lot of photonic functions in one single chip. It uses the standard processes from Semiconductor, so this is much easier to produce and cost effective. If you look on this typical 5 parameters of disruption, or at least photonic integrated circuit has impact on all of these 5 parameters. It changes scalability, cost, size, performance, and energy consumption. This is, you can imagine every single of this parameter. If you change this dramatically, this will change also your business. This will change your product. And if you combine them, even if you have all of them changed, then this can really create new markets and disrupt a complete company. So let's go to them with a very specific example. Here is an example of OCT, the optical coherence tomography device, and it's used by the ophthalmologist to check your eye, check the retina, check whatever eye diseases. And you see, it's a very bulky device. It's this size around, and it's a tabletop device. And there's a lot of photonic component, optical component. It needs a lot of adjustment in production. And it's already the first point, scalability. Not having all this adjustment needed, all these single components in production, we can produce on the same footprint 3 times more devices with no additional effort. The cost reduction, that's I think the most impactful point. It's not a factor of 10 because we have so many single elements in such an OCT that the OCT engine have a cost reduction for around about 50 to 100. Also it's the factor, not percent. So it's a complete different story that we can do with this. And here, oops, sorry, I forgot to. Here, this is the pointer's not working. This is the OCT engine that is actually 70% of this volume. It's here in 7 millimeters of a peak. And here is also together with the optics element here in front. And this is also then, you see here the miniaturization. So it's less volume dramatically less volume. So it's not about that we can build this smaller. That's also fine, but you can think about complete new application, mobile devices, whatever. And so also for high performance. It's not only that we implemented one of this OCT in one chip, but we implemented actually 4 of this OCT engine in one single chip. So you can improve the quality, comparing the results, you can improve speed and so on, so reduce also the time the patient has to be in front of this. And last but not least, low energy consumption, especially if you look in new application, this can be very helpful. So now, if you transfer this and look, okay, on Europe, what happens in Europe with this? That's because it's not, that's one example. Let's look this not as a medical product only, but really as a pattern. If you have photonic products in your portfolio, this could be really a game changer, a disruption potential. And if you look now in Europe, because the race for PICs is not yet done, so it's not decided who wins the complete field of PICs. And in Europe, we have this typical behavior that Europe invents, then others scales, and then we buy it back, often much higher than we could do it on ourselves. And I want really to encourage you all that are somehow connected to photonic to go into this topic. It's really worth, because we have a great ecosystem in Europe. We are leading in publication, in quality of publication in PIC, and it's important that we can use and transfer this invention to innovation. It's really the opportunity in Europe we have, and I can only encourage you to do this, because we have a great ecosystem, and it's also as size, we will not, or we don't want to own the complete value chain. It's really, okay, let's partner in this topic. It's too complex to do all on our own. We are fully aware that we have to partner with this, and we have a great ecosystem, so think big, and let's build together our photonic integrated circuit powerhouse. Thank you very much.
Thank you so much. That was excellent. Are there any immediate questions, or shall we proceed? I think we'll keep going. We'll keep march on. Thank you so much. So I think that was quite inspiring. I feel like opportunity in Europe, invention to innovation, and the role of long-term innovation is critical. And for our next value chain speaker, we're going to hear from Amir Gadimi, who is CEO and co-founder of Litium. It's a Swiss startup enabling the next generation of photonic integrated circuits with their foundry services, from rapid prototyping to volume production. So he's going to tell us more. Please welcome on stage Amir.
Thanks so much. Thanks for having us. So let me see how it works. So I have to thank Michelangelo, because he sets perfectly the stage of why we need PICs in Europe. And let me tell you a story of actually how we are trying to commercialize and actually keep the manufacturing of PICs. So my name is Amir. I'm actually the CEO and one of the co-founders of Litium, which is actually a Zurich-based startup. And we are trying to really commercialize a new, PIC technology based on a new material called thin film lithium niobate, and how we are setting up the TSMC of photonic in actually Europe for this technology. So let me start by saying why should you care, or why this material platform is interesting. I mean, and really there are many applications in PICs, and Michelangelo mentioned about something about in OTC, but I would like to start with something maybe more urgent and more bigger in scale, is actually the AI infrastructure, which is right now in strain. So as again, I think it's been discussed in this conference quite a lot, that AI is kind of almost reverting everything we did for carbon capture in the last 3 years. And currently, if data centers that are actually enabling this AI photos that actually this conference generated, it's actually, if they were a country, they would have been the 5th biggest consumer of electricity, a little bit over Germany, right? And it's growing in a very scary way, because by 2030, this will be 10% of the global energy consumption. And by most model predicts that actually by 2035, the data center will surpass the whole union energy consumption, right? But let's see what's behind this thing. So if you kind of go into this, sort of data center, and one of these, racks is now, made in NVIDIA, $5 trillion company. It's made of several compute nodes. Typically, in this one rack, you have, 72 GPUs, because we cannot just fit one AI model in a single GPU. And what is the situation is that, we have a lot of these, NVLink switches, about a 3 kilometer of fiber to actually, and this sort of GPUs, transfer ungodly amount of data between themselves, so they act as one big GPU. How much we're talking about? The 200 terabit every second. Just to put it in perspective, that's about 1/4 of the entire global internet traffic. Every second goes up and down this rack. So this 72 GPUs act as one GPU. And this up and down is, account for about 25% of the energy and about 3 kilowatts of power. 3 kilometer power, 132 watt power. This is not scalable. Of course, we have to change this drastically. And photonics, actually, photonic chips and fiber optics networks are trying to sort of replace that. And currently, actually, the material of choice to making this pluggable module, about 200,000 of this in a average 100 megawatt data center. If you open them up inside, you have a chip like this, which turns the sort of a light, and the functionality of it is no greater than just a light switch and you have in your in your wall. It just turns the lights on and off. If you could just turn this light switch like 400 billion times every second, right? So people have been making this sort of mostly out of silicon, but then we are, as the demand for AI, we are reaching the end of silicon. It just cannot keep up with the demand of AI, and it's not the most power efficient material. That's where lithium, over the past decade, based on my own research, we pioneered a new material. It's kind of a magical type of glass that when you apply electric field, is refractive index changes, and that's how we control lights electronically on the chip. And this allows us to go much, much faster beyond the limits of silicon. So at Lithium, we set out to actually commercialize this platform, and now that actually is AI, as I mentioned in the first opening, compute is becoming a commodity in data centers. The limit of the AI scaling is now how much data you can actually send between the memory and the GPU. So this optical interconnect, which was kind of a niche, is more like, sort of nobody take it seriously. It was more for a bunch of nerds. Now it's becoming a very mainstream, right? And so now it's like everybody is like, almost NVIDIA is putting, investing in anything as a photon in it. And this becoming very interesting. And this material is now becoming, so like a gold. It's actually these wafers, once we finish them, we sell them, at their weight in gold. 25x. So if you turn them into pure gold, we lose 95% money, right? However, there's no TSMC of this, right? So if you want to make a silicon chip, you just go to TSMC or Samsung, and then they'll make it for you. For this type of chips, there is nobody, and this is what Lithium set out to do. We are a zero-risk-based foundry. We are not a product-based. We don't have any product of ourselves, but we make everybody's product based on this platform in high volume. So. Of course, so I started my pitch to saying that these chips enable these data centers and interconnect, but it's not the only one, right? Of course, one of the main things is 1.6 and 3.2 terabit, transceivers. But on this same wafer that I showed in the last slide, you see actually there are multiple different type of chips. We have also same chips on the same wafer that actually have quantum computers in it, and also optical computing, as well as aerospace and defense. An area, these chips are extremely now on demand. So we're making almost 1/3 of our revenue from aerospace and defense. And what we offer at Lithium is actually everything from prototyping, so starting from an idea, all the way to very high volume manufacturing. And by high volume, I mean 1,000 wafer per month. So about a million chip a month of production. So how does our business model work? So we actually, so as I mentioned, we are equivalent of the TSMC of photonics. So we are not a product company, we are a sort of foundry. We design internal, this is sort of from our own clean room in Zurich. We design, which in our clean room in Zurich is not a production clean room. We are just doing, sort of R&D and prototype and process development. We designed something we call the 100G node. So it's a 400 gigabit per second switching time. And the whole IP around it, the cross-section, the process flow, the recipes, as well as also whole design kits. So if you are a customer, you go to TSMC, you want to design a chip in 5 nanometer node, they give you a 5 nanometer design kit. If you come to us, we give you a 400G node. But a customer, right, like somebody like Zeiss designed their own system, like somebody. So we give them all the Lego pieces, and then you combine them. One chip becomes a computer chip. The same component you design and assemble in a different way becomes a transceiver chip. So we get this design, then we do further processing, And then essentially we make all the processing, and then we send it to our subcontractors. So we are now having an exclusive contract manufacturer in the US. Sadly, we could not yet scale it to Europe, and we are now trying to bring this sort of manufacturing back also to Europe. But once the wafers are done, the full wafer, it comes to our facility in Zurich, and then we do, actually the hard part that starts, which have to do design and test and validation and verification of these chips actually works. So we do test and verification, quality control, and then we singulate this wafer into little chips, and then we send it to customer, what we call it a good known die. And over the time, we build one of the most state-of-the-art testing houses in Zurich. We can do everything from chip scale to wafer scale. And over the past 3 months, so we founded the company in September 2023, and we've been growing very fast. So we raised so far about $12 million seed round. The technology works. So this is 400 billion times a second switching light. We put 4 of them, it becomes 1.6 trillion times a second chips. And we're a team of 27 people. And now we are sort of building on this strategy of dual supply chain, one in US and one in Europe, and our in-house test and functionality. So these chips maybe take a few tens of dollars to manufacture. It takes about $150 to be tested. So it's actually, that's really where the money is, sort of value is added. And as mentioned that actually over the years, again, it's for us, when you're in a business of chips, as I think also Michelangelo mentioned, we are really good at actually making technologies and innovating, but horrible typically when it comes to the scaling, right? Again, it's a sort of self-criticism. We should actually take it, and the first, always say the first step of change is to actually accept you have an issue. So this is what we've been working. So when you're working with a chip, if you work on a technology that is not scalable, it doesn't count. Its value is no more than a wafer. It's more than a paper, right? It becomes a product when you can actually manufacture it in volume. That's the only thing that actually matters in photonics. So, or semiconductor in general. So we build a very, how to call it, secure supply. It's actually a global supply chain. These wafers, if you attach a mileage in it, they actually collect more mileage than an average European. So they pass through different factories. So you have a front-end fab, you have a mask shop, you have front-end fab, back-end fab, and then everything comes to Zurich, and then we actually qualify that they are within the how to call it standard that we define. And what we really, the reason actually the customers working with us, because these Lego pieces that we give them is really a kind of well tested, and we can actually prove that it works with a very, very high reliability across the different wafers and wafers. And finally, over the last years, we built our sort of team. I'm happy to say that actually now we can deliver our first chips to our sort of customers, and now we are signing the first how to call it long-term manufacturing contracts. We build our leadership team. So if you're interested to learn more, just visit us at booth number B06, which is in the exhibition area. Some of our actually sort of key management team are also here, Kevin in the audience, and then the rest on the booth. And with that, I want to thank you for your attention and happy to answer any questions.
Oh, good. We have a question. Go for it.
I wanted to ask, since you showed us the supply chain picture, so what part of the supply chain, especially also what part in the future, do you see in Europe, and what part do you still see in the US and in other countries?
I mean, to be honest, currently everything which is kind of design, raw material, design, and verification is done completely in Europe, right? The R&D of the production is also done in Europe. We haven't yet made, we are kind of millimeter away to giving it up, that actually manufacturing volume in Europe, but we are really trying. So the front-end and back-end fab right now in 200 millimeter volume is in the US. We've been trying to actually sort of convince other fab. Our business model is not to build an infrastructure. We much prefer to walk into somebody who has a fab, and most of the European fab have excess capacity and just rent capacity and install our nodes so they can run it as a contract manufacturing. So right now front end, back end, but everything is actually everything else is done in Europe. Right. Any other question?
I think we'll proceed. Thank you so much for that excellent
so
presentation. All right. So, no, I mean, come on up here. So Yeah, I think that was really interesting about the TSMC of photonics and how to scale and how to run a foundry service. So we are going to walk further through the value chain now. So I'm happy to welcome Andy McInnes, who is Chief Development Officer of Paragraph. With headquarters in the UK, Paragraph is the first company globally to mass produce graphene-based electronic devices using standard semiconductor processes. They leverage a proprietary materials process that's designed to enhance performance, efficiency, and functionality across advanced sensing applications. So, welcome to the stage, Andy.
Thank you. Yeah, good morning, everyone. Just like to do the very nice segue that Amir set up. Paragraph, we'd like to be the TSMC of graphene. So thank you for stealing my thunder. Very well done. Paragraph is a UK company. We are talking here about building European infrastructure. I believe the UK is still part of Europe, despite some of the recent kerfuffle. And we would like to really be part of that ecosystem and really build the relationships here. On a more personal note, I should just point out that I've spent the last 35 years working in the US, and particularly sitting in Sherman, Texas, looking out the window of my office and watching TI build a facility in 2 years, which is basically the size of a small town. This is a mammoth task for Europe to recapture a lot of this technology. Fortunately, what we're hearing this morning is areas where really US does not have a competitive advantage. There are new technologies where we are taking the lead, and we're going to drive that scale up, and we're going to drive that technology home. And that's really what we are trying to build here with graphene. Sorry, does it? Is this not? Oh, sorry, there we go. So we are a UK-based manufacturing facility. We do claim to be the first graphene manufacturer in the world. That's a 6-inch wafer that comes from our brand new facility just outside Cambridge in the UK. It's on a silicon wafer. It's got graphene on it. It's a molecular sensor wafer. These will be packaged up into SOT23, QFN, sold. You can buy them on our website. We have sales generated from these wafers right now. TRL level for this product is maybe about 7 to 9, and we'll expand upon that later on. What we do in that facility, and it's a brand new facility opened this year. Paragraph is a company of about 110 employees. We are through Series C in funding. This building is only partially occupied. We're opening it in stages based on the funding that we receive. We've built previously in what is now our R&D facility, we've built Hall sensors, and I'll talk a bit about those later as to why graphene is an ideal material for those. Molecular sensors, just shown you a 6-inch wafer, which is now mass-produced. But really our goal is to become, again, the TSMC of graphene. We want not to be the product experts, we want to be the process and growth experts for which a European infrastructure or even a worldwide infrastructure can access and leverage off. Quickly backtrack a second. Why graphene? What is special about graphene? We hear it everywhere. First theorized back in the late 1940s as part of the nuclear age. Researchers in Canada theoretically modeled graphene and were just blown away. It's got, in theory, incredible properties. It's a material of superlatives. It's the most conductive material known to man. It's the strongest material known to man. Thermal conductive, it's up there as well. It's inert. It's biocompatible. It's carbon. You can put it in your body. Graphene is if you pull a single layer of graphite, that single layer of carbon, so one atomic layer thick, that is graphene. So Mother Nature has given us a tremendous gift. However, Mother Nature giveth, and yet she doth taketh away as well. It's an atomic layer thick. There is no bulk, it's two surfaces. Anything you do to that single layer impacts it. Breathe on it, impacts it. Again, the material is superlatives, but an incredibly difficult material to deal with. So what makes paragraph unique? We are not the only people in the world to make graphene. In fact, Europe had a 2D pilot line, a lot of infrastructure to exploit graphene. Most of the world deposits graphene on copper. Copper is a catalyst for the growth. You get very pure graphene, but it's on copper. You then have to work out how to get it off and put it on the real material that you'd like to put it on. Silicon wafer, gallium arsenide wafer, silicon photonic waveguide. What the core IP within Paragraph is, we do not grow on copper. We grow on electronic grade substrates. So that very first step, and anyone who's worked in an electronics fab knows we wear bunny suits, we filter, we try and remove every possible contaminant in a semiconductor environment. In this particular case, most of the world deposits on a foreign substrate, which is a contaminant in the electronics industry. So we have got past that hurdle by doing a direct growth. Simpler, cleaner. I've got some dots here, tunable. What this allows us to do, it allows us to choice of substrate, different orientation, different offcut, different base material. We can prep the interface in situ. We can reconstruct surfaces. We can design an interface. That also enables us to remove this material with incredible ease. So this second part, where electrolysis or other chemical methods that are used to remove that film from copper, can also be achieved here. And when we do that, we find that we get no degradation in the material whatsoever. So this material can be grown on 2-inch through 12-inch substrates. It's a single atomic layer. It's 100% single layer. It's 100% contiguous. Contamination-free. It has never seen a metal at this point. High peak mobilities. In the graphene world, everyone measures it differently, but comparing apples to apples, that's a very high number. This is the equivalent of your microprocessor getting faster and faster speeds. The ultimate determinant of a semiconductor performance is its mobility. How fast can those charge carriers move? Silicon, for reference, is around about 1,000. So these are materials, advanced materials, which show incredible potential, but again, single layer material, very difficult to handle. Just showing some of the common metrics here for graphene. A Raman spectra shows it's contamination defect-free. It basically means all those little 6-membered ring hexagons are pretty well intact. Graphene performance is not determined by the 6-membered rings, it's defects in those 6-membered rings. That's carrier scattering. As with most semiconductors, it's limited by its defects, not its bulk or surface properties. So our graphene, we can grow large areas, we can grow directly on electronic materials, we can actually take it off electronic materials, put it on another surface, and retain its property. So what do we do with that? Well, currently, if you go to our website, you're really going to see a couple of different device platforms. Hall sensors. Hall sensors are determined by mobility and carrier concentration. Graphene has the properties that suggest that this is an ideal application. Potential uses in electronic vehicles, but at the moment, they're still more expensive than silicon, so it really hasn't broached that market yet. Cryo compute, where you do measurements at millikelvin range, almost absolute zero. These devices work in harsh environments. They're radiation tolerant. They work in high fields, low fields, absolute zero through elevated temperatures. Molecular sensor. That's the wafer I just showed you. And this is what you will get from Paragraph if you go onto their website. A GFET, a graphene field effect transistor, is basically graphene as the channel, source drain. When that surface is functionalized, such as an aptamer or a membrane, any material that hits that surface, the graphene can detect the charge caused. This can detect down to femtomole range. To put that into perspective, that's 1 grain of salt in an Olympic-sized swimming pool. These are aimed at healthcare, biosensing. We're showing an example of potassium sensing for kidney disease monitoring. They can be real-time, but in healthcare, they're mainly disposable. You cannot expose a bodily fluid twice. We sell design kits right now. That's a test chip. Plug it in. You can do your own development. When you have got that development done for your specific analyte, you come back and we'll make it in volume for you. If you want to go to someone else who handles graphene, you can do that as well. That's our standard products. This is where we're going. So this transcends a lot of the issues you've been hearing about this morning. This is one of our devices using the quantum capacitance of graphene. The unusual band structure of graphene gives it weird and wonderful properties. You can tune capacitance in a single material. This should work up to terahertz range. This is an RF varactor. Same ability to tune capacitance or refractive index allows optoelectronics, waveguides, modulators to be developed. We've heard earlier about quantum compute. This is not the trapped ion. This is a different either spin charge coupling qubit. It's a different approach, but again, graphene is heavily involved. Graphene or bilayer graphene has persistence in quantum states. It's one of the many approaches to quantum that's being developed right now. Then the ultimate goal, neuromorphic computing or memory. We've demonstrated incorporation of graphene into ferroelectric memory. We can incorporate it, it switches. The graphene is not active in that device. It gives persistence to the ferroelectric state. It makes the device a lot better. It makes it last longer. These are all TRL up to about 3 or 4. This is where we're going now. We're collaborating with external sources. The source of this is the quality of the graphene that we produce. That's our claim to fame. We're not device experts. We do the demonstration. Other people take it from there. So just to finish up, this is our general technology roadmap. It mimics the roadmap of many other electronics and photonics houses. Again, we're not the experts. We're the experts in the growth and the processing of this wonder material. If you see your material on that sheet, we'd love to speak to you. Paragraph, we do have a USA office, boo. It's an applications lab, but we are based in the UK, and we now have sales offices in the Middle East and Asia. So we're trying to export this worldwide. We are going through funding, we're going through collaboration. Let's continue the conversation. Thank you.
Thank you, Andy. Any questions right now while Andy is still on stage? Yeah, let's hear it.
Yeah, so obviously, are there real products out there already?
Yes.
Semiconductor products?
Yes, so there are products out there already, mainly in quantum compute. The devices, the Hall sensors are used in a millikelvin range to do the background field subtraction in qubit field calculations. There are other niche areas. The molecular sensors are highly developed right now, and there are use cases that are being trialed. It's really waiting to happen. Some of the newer technologies, can't talk about them here, but we are in advanced development with some of the bigger players in the industry. So that is the bigger prize. And again, it's our material that's opening these doors, and that's where we expect to advance through those newer technologies that I showed.
I would just have one question, because you said that the US does not have technical advantage, meaning what's happening with graphene there?
They do make graphene. There are plenty of materials, plenty of universities, plenty of development organizations. You just heard from Black Semiconductor earlier today.
Yeah.
That is one of the biggest bets in graphene. And I think anyone who missed that talk, it's a very impressive bet on graphene. We do not compete with them. We hope to complement or even support them, and vice versa, they could support us. But there are no clear black semi equivalents in the US right now, or even paragraph equivalents, to the degree that a lot of the companies we're dealing with are based in the US simply because they do not have the same access to the technology that we have here.
Amazing. Okay. Thank you so much. All right. Thank you. All right. So we're marching forward. We've explored innovative materials, and our final perspective comes from Marta Ostromov. I hope I'm saying that somewhat right. You can correct me. Who is the CFO of Accelera AI. The company has developed a powerful AI-native hardware and software platform for edge computing. Headquartered in the Netherlands and with R&D offices and operations across Europe, their team consists of experts in software and hardware to accelerate AI. So, welcome, Marta, to tell us more.
Thanks very much for having me, and thank you to all the speakers. It's exciting to hear all this knowledge and science being developed. I want to take a step back and talk a little bit about why we're here. So the world is changing around us extremely fast, faster than most institutions can process. AI has become the industrial infrastructure, and the companies and countries that build it will set the rules for the future. And I hope this is Europe for us. So we have a genuine choice to make, and that is, are we ready to build the industries that will take this innovation forward for decades? And I would like to make the case that that's absolutely possible, but there's a missing ingredient, and I'm a CFO, a lot of people come forward and say there's lack of capital, shortage of capital to innovate. I don't think that's entirely true. 20 billion is invested annually in Europe in the deep tech AI procurement. That number is going to go up to 100 million, that's the ambition, certainly set, by 2030. And how do we close that gap? And the gap needs to be closed not by the science, we already have it, not by the talent, we also have it. The capital is also flowing, funding this innovation. It's the deliberate demand that needs to exist in Europe. We are great at breeding innovation, we are great at funding it, solving the hard problems, but we are not so great at buying our own technology. So that's what needs to change. So what is Accelera and where we sit in the AI stack? You can very simply imagine AI stack split into 3 layers. You train a model, you deploy a model, and in between there's an infrastructure that enables inference acceleration. So that's the point at which AI hits the real world. And that process, the infrastructure, the middle layer, needs to be such that enables that acceleration to be done viably, it needs to be economically viable. That's where Accelera comes in. We sit in the middle, we design the chip and we build it, but we also provide a software platform as a combined solution. So I'll take the cost element of deploying AI model a little bit further, because what we're seeing today is the inference infrastructure is completely built on GPU architecture, which is designed for cloud data centers. It's expensive, and it requires enormous amount of energy to support it. Now, it works brilliantly if you have access to hyperscale data center, but if you don't, and you have an infinite energy budget, but if you don't, then you can't scale AI. So our solution provides power efficient and cost effective inference acceleration so that the deployment of AI models can be done profitably. And that's really important. Very quickly, what we do, what products we have in the market. We are European Eindhoven-based semiconductor business. I've talked a little bit about what we've done. We haven't just built the chip. We've built the chip, the hardware, and the software layer that goes with it, which together gives us a turnkey solution to deploy models at scale profitably. So if I break it down a little bit into the technology, our technology is based on a unique architecture, which is called digital in-memory computing. And what that means is that we are able to provide and drive GPU-level performance at fraction of the cost and fraction of the power consumption. This is exactly what AI stack in Europe needs. We have a silicon in production already. Product is called Metis. You can hop to our website and buy it. That was commercialized in late 24. We are in full production already today. We've got a pipeline of 500 plus customers. Second silicon, Europa, which is more near-edge server capacity product, is being launched very soon this year. And the third silicon, which is HPC data center type, is in development due to tape out in late 27. Above that technology sits a horizontal software layer, which enables viable, fast deployments of the technology. Seamless deployment is optimized for common workloads. And you can bring your own model, or you can use ours. So it really accelerates that inference process. And what that therefore enables is deployment everywhere, but in real life settings where energy consumption and cost matter without compromising the performance. So here's some stats. I wouldn't be a CFO if I didn't show you some output. Our performance is 2 to 8, and this is a big range, and we can talk about that a little bit, 2 to 8 times higher than a competitor equivalent platform. Power efficient 4 times X, and those are numbers that actually our customers bring to us, and we are 3 times more capital efficient. So what I'd like to do is train your eyes to the bottom on the right-hand side of this slide, because this is actually the savings that our product generates for the users, for the customers of our technology. So if I compare Metis to NVIDIA Jetson family, saving over 10,000 units per year equates to just under 10 million. And if we segue to Europa, which is the server, enterprise server type of product, that goes that goes up significantly. As I mentioned, we've got customers. Pipeline keeps on growing. There is a real recognition of the European design and development that we've achieved. So you're seeing some big names that we're working with, and we've been very successful. But how have we got here is not, it's not been pure luck, obviously. There's a lot that goes into engineering this fantastic technology. So I'd like to just give you my CFO view on the economics of where we've got to. We are just over 4 years old. We taped out 4 silicons in 4 years. In semicon, that's an unheard of timeline. We are $500 million backed, $500 million, both from sovereign capital as well as private capital. But the first 80 million, which is quite unprecedented in terms of the quantum because it's a low number, was invested in the first chip. We are already profitable today, so we've designed a product that can be sold with a profit margin, and so our economic model works, and therefore that fuels the investment that keeps on flowing. But we don't stand alone. We are not a single scale-up corporate business that tries to tackle the semicon industry. We are part of a very rich ecosystem of partners. We partner with IMEC, we partner with ETH Zurich, the heritage comes from there. We are very much part of European Commission Research and Development Consortium programs where we contribute our technology towards the innovation side of things. And you're seeing, again, some big industry names here that we solution for the future together with. So my final point, just to circle us back to why we're here and what this summit is all about, is we're here to make a choice, not in 5 years' time, make a choice now to procure our own technology that we so hard worked on funding and developing. Europe has the science, we just have to buy the results now. Thank you very much.
Any immediate questions? Oh, good, we have one.
In terms of customers, you're very clear about like buying from European companies. In your current pipeline, how much of these companies
Very good.
are actually European? And
Yes.
how much are currently US customers?
Very good. So I would, without disclosing too much confidential data.
Sorry, I didn't. Can you repeat the question? Apologies, but I really want to listen in.
That's okay. I'll repeat the question. So the question was, we have 500 customers in our pipeline. We are a European-based business backed by sovereign capital. How many of those 500 customers buy our technology? And the split today is 50-50. The US market, Americas are growing rapidly because those guys are more risk-taking, they're looking for new solutions, and they are prepared to adopt AI much faster than Europe can. So we would like to see in the next 5-10 years that ratio switching. That's why we're here. That's why we're presenting to you all, because Europe has the science and the product. We just don't buy our own output that we fund. So that's the message. But it's very positive to be hearing all your talks and where we headed. I think we've got all the ingredients. We just need to commercialize it.
Thank you.
Thank you.
Amazing. Thank you. All right. Thank you guys for your attention. I'm just going to leave you with 4 takeaways from this session. I'm just going to go right in order here. And I think that was nice to end on this note of ecosystem collaboration that she just spoke of. So here we go. From Michelangelo, I'm taking away the role of long-term business innovation and that there's a paradigm shift of photonic integrated circuits that can truly disrupt photonic business. From Amir in talk 2, I would share that we're at the golden age of photonics. That means optical interconnect is one of the most important gatekeepers in the AI boom. Photonics enables the next generation of high-speed interconnects in data centers, and Europe might have a real chance of leadership here. And thirdly, from Andy, established baseline graphene manufacturing practices can now enable entry into AI-targeted products. And finally, thank you from Marta. There's a need to take collective responsibility to adopt European innovative technologies, and this will fuel deliberate demand for European companies to scale. So with that, thank you for your attention and your time, and next up we'll be hearing about advanced materials. Thank you all.